Today we are going to extend our discussion on the method of power series to solve ordinary differential equations, and specifically we are going to bring in the modified power series method named after German mathematician Frobenius. Okay, so you may ask, what is a modified power series? This is what we call as a power series centered at the real number x0. Okay. Now you may recall from the calculus of complex variable functions that we can allow negative integral powers of the term z minus z0, and such a series is known as Laurent series. Okay. Now in a Laurent series, the power of z minus z0 can be negative, can be positive, or it can be 0, but it has to be an integer. Okay, but in the modified power series method, we are going to multiply the entire power series by some power of x, where this r can either be any real number or it can even be a complex number. Okay, so the powers no longer remain non-negative integral powers. They can even be fractional depending on what you choose r to be. Okay, once we discuss it, then we will go to the classification of singular points into two types. Okay, and then we'll of course solve the questions on that classification of the singular points of the functions, and then we will discuss the main idea behind the Frobenius method or the modified power series method and its connection with the Euler-Cauchy equation. Okay, if you recall, the Euler-Cauchy equation, the differential equation of second order, is in this form: x squared y double prime plus some constant p naught into x into y prime plus some constant q naught times y equal to, well, you do have a function, but let's take it 0. Okay, because currently we are discussing only the homogeneous differential equations. So we'll see how these two things are connected to each other, and then we will solve an example which is going to take a lot of time. Okay, so this is what I'm planning to cover today or in today's session. Okay, let us now start discussing the Frobenius method, which is due to the German mathematician Frobenius. Okay, we call the Frobenius method to be the modified version of the power series method because of the following reason. Okay, by power series centered at x0, we mean this: summation as n runs from 0 to infinity an into x minus x0 to the power n. Okay, now if we modify the power series, okay, then the modified power series is in the following form: centered at x0, Sm, let us say, equal to x to the power r into summation as n goes from 0 to infinity an x minus x0 to the power n. And to solve the problems by the Frobenius method, conventionally we write the power x to the rth power of x inside the summation notation, so we let it as summation as n goes from 0 to infinity an multiplied by x minus x0 to the power n plus r. Okay, so I should have written x minus x0, sorry, here. Okay, so this is the modified power series, and r can be any real number or even complex number. Okay, fine. Now our whole objective in this problem, or in the Frobenius method, is going to determine two things. Okay, the first job is to find the values of the coefficients a n, obviously, and this is what we even did in our original unmodified power series method. And second is to determine the value of the unknown, I would say unknown constant r. Okay, now we are required to solve a quadratic equation to find the values of r, and that equation is known as the indicial equation. Okay, for a second order differential equation, it is a quadratic equation. Okay, now in the Frobenius method, what we do is we actually expand the power series, not about any point where the function is analytic, but we expand it about a singular point. Okay, which means either p of x or q of x or both will not be analytic at that particular point, okay, or x naught. Now you may ask, what's the whole purpose of expanding both p and q, as well as the other things, the unknown function y and its derivative about x naught? Well, the answer to that question will become clear later as we solve the problems. Okay, now the point common to this method and the original method is the calculations that are required or that are supposed to be done or supposed to be performed. All these calculations can be done by the software once we get the recurrence relation. Okay, so that is the power of the Frobenius method. It is capable of solving those differential equations which can otherwise not be solved by the methods developed in our previous discussions. Okay, so first let us see how we can classify the singular points. Okay, we classify the singular points into two categories. The first is the regular singular point, and the other category is irregular singular point. Okay, and throughout our discussion on the Frobenius method, we will be focusing only on the regular singular points and not on the irregular singular points. In fact, when we expand the power series about a singular point of either p of x or q of x, it is required that the point is a regular singular point. Okay, so we start with the given things, okay, which are required to define these two singular points. We start with our standard ordinary differential equation of second order, y double prime plus p of x into y prime plus q of x into y equal to 0, where both p of x and q of x can either be constants or functions of x. Okay, now in this chapter we will see situations where both p of x and q of x are functions of x. Both will contain at least one term in x, okay, because we already know how to solve linear ODEs with constant coefficients. Okay, the other thing that is given to us is a real number x naught, which is a singular point. Okay, now this point can either be a singular point of the function p or q or both. Okay, and how do we determine the analyticity of any real function? Our way of checking analyticity at a point is we check for the existence of derivatives of all order of the function. Okay, and even if either p or q does not possess a derivative, or if it is not defined even at that point, we will call it a singular point. Okay, fine. Definition 1, regular singular point. So when will we call the singular point x naught to be a regular singular point of the ODE? We will call it a regular singular point if x minus x naught into p of x, okay, and x minus x naught squared into q of x are analytic at x naught. Okay, so we already know that at least one of these two, p of x and q of x, is not analytic at x naught. But if you multiply p of x by x minus x naught and q of x by x minus x naught squared, and if you find that both of them are analytic, then we call such a singular point as a regular singular point. Okay, and definition 2 depends on the definition 1. We call x naught an irregular singular point of the ODE if it is not a regular singular point. Okay, so all those singular points which are not regular, they are irregular singular point. Now we will not talk much about the irregular singular points. Our discussion will be only focused on regular singular points. Okay, another thing, throughout our discussion we will be considering functions which possess singular points at 0. Okay, so if x naught is taken at 0, then the power series looks a bit easier. Okay, we don't have x minus x naught to the power n, but we always have x to the power n. Okay, so if x equal to 0 is a regular singular point, then x into p of x and x squared into q of x, these will be analytic at 0. Okay, now if these two are analytic at x equal to 0, this implies that we can now bring in their Maclaurin expansions. Okay, this is important because we are going to make use of this fact. Maclaurin expansions exist. Okay, so regular singular point means x into px and x squared into q of x, both are analytic, even though the original functions may not be analytic at that particular point. And if these two conditions or criteria are not met, we call that singular point as an irregular singular point. Okay, let us now solve some examples on this. Question 1. Identify the type of singular points of the differential equation x into x minus 1 squared into y double prime minus 3y prime plus 5y equal to 0. First, we write the differential equation in the standard form, which is y double prime plus p of x into y prime plus q of x into y equal to 0. Now to do this, we are required to divide the entire differential equation by the coefficient of y double prime, that is x into x minus 1 the whole square. Okay, so on doing that, our p of x will become negative 3 upon x into x minus 1 squared, and our q of x will become 5 upon x into x minus 1 squared. Now clearly these two are rational functions. Okay, so the rational functions are singular at those points where the denominators go to 0. Okay, now both have the same denominator, x into x minus 1 raised to 2, and this function has two zeros, x not equal to 0 and x not equal to 1. Okay, now to check whether 0 is a regular singular point, what we should do is we should multiply both p of x and q of x by x and x squared respectively as per our definition. Okay, now if we multiply p of x by x, then we are going to get minus 3 upon x minus 1 squared. Yes, and if we multiply q of x by x squared, we are going to get 5 into x upon x minus 1 squared. Now although the new functions that we have got, they are still singular at x equal to 1, we are now, at least in this particular discussion, not interested in x equal to 1 because we are looking for analyticity at x not equal to 0. Okay, so are x into p of x and x squared into q of x analytic at x not equal to 0? Yes, they are, because they are rational functions and denominators of them do not have a 0 when x is 0. So x is equal to 0 is a regular singular point. Okay, now let us go to the next singular point, that is 1. Now to check for the analyticity at 1, we are required to multiply p of x by x minus 1 and q of x by x minus 1 raised to 2. Okay, if we do that, in p of x or in the product, we still have x minus 1 present in the denominator. Okay, because in the original definition of p there were 2 powers of x minus 1. Yes. Now this itself classifies x equal to 1 to be an irregular singular point, because x minus 1 into p of x is still not analytic at x equal to 1. But let us do it for q of x. Okay, so let us multiply q of x by x minus 1 raised to 2 the way we did here. Okay, now this actually leads to the cancellation of x minus 1 raised to 2, so we get the function 5 upon x. Now this is analytic. Okay, x minus 1 squared into q of x is analytic at x equal to 1, but we will not call it to be a regular singular point because of this. Okay, not analytic at x equal to 1. Okay, therefore x equal to 1 or x not equal to 1 is going to be an irregular singular point, because x minus x naught into p of x is not analytic at 1. Okay, so you may get a 2 or 1 mark question based on the identification of the singular points and their classification into regular or irregular singular points. Okay, question 2. Identify the type of singular points of the differential equation y double prime plus root of x into y equal to 0 with x non-negative. Okay, now here the coefficient of y double prime is 1, so there is no need to perform any kind of division. Okay, and also there is no term containing the derivative y prime, so we may assume that p of x is 0 and q of x is root x. Okay, now p of x being a constant function, it is analytic everywhere. Yes, but as we have discussed already, q of x, which is root of x, is not analytic or singular at x not equal to 0 because the derivative of q is 1 upon 2 root x, which is not defined at x equal to x naught. Okay, so clearly 0 is the only singular point of this differential equation. Now we need to decide whether it is regular or irregular. To do it, we multiply p of x by x, which still doesn't change p of x because p of x is 0 throughout. Okay, now let us go to q of x. Okay, we are required to multiply it by x squared or x minus x naught raised to 2. Yes, q of x is root x, so if you multiply root x, okay, by x squared, you are going to get x raised to 5 by 2. Okay, now x raised to 5 by 2 is a function whose third derivative doesn't exist. Okay, let us see. First derivative will have the power 3 by 2, second derivative will have the power 1 upon 2, and the third derivative will have the power negative 1 upon 2. Okay, so q triple prime of x doesn't exist at x not equal to 0. Yes, so it is an irregular singular point. Okay, so a singular point has to be either regular or irregular. If it is a regular singular point, it has to be a regular singular point of both x into p of x and x squared into q of x. Okay, all right.